I forgot to mention something in the end of the last video, and that is that the trapezoid decomposition has linear size. We can easily see this because we can just count the number of vertices of this trapezoid decomposition. We have n original vertices, or 2 times n original vertices of the n line segments. Then from every vertex we go up until we hit a vertical line, so that creates one vertex here and another vertex over here, right? So I had 2 n vertices, and each one creates another at most 2 extra vertices, so that's for a total of 4 times n vertices. And since it's a planar graph with a total of 4 n vertices, the size is linear. Yeah, so that's quite easy to see. Okay, so now let's look at the real question. How do we build a search structure? And remember that the search structure also builds a trapezoid decomposition. Alright, so there is no gentle way of explaining it, even though the main idea is very simple. We want to build a search structure which is not going to be a tree. So this is one of the rare examples where we build a search structure that is not a tree. So this is technically a directed acyclic graph, or a DAG. What it means is that you have loops. So let me just show an example of it. So for example, this could be one search structure, and if you look at this, you see that to get to this leaf, I have 2 paths. I can go this way or this way. So this is not a tree. I think the best way I can explain this structure is using this gadget. This is not how it's explained in the book, but I like my explanation better because I think you can think of it as a generalization of a one-dimensional search structure. Forget this picture. Let's look at 1D and then see how we can generalize it. In 1D, how do we do binary search? I do have n values here. How do we do binary search? You pick one of them, the one at the, let's say position I, which is roughly n½ and you put it at the node, right? So this, you have EI. And then when you want to do a search, you do a comparison. If it's less than EI, less than equal EI, you go this way. If it's bigger than EI, you go that way, right? So that's how your search structure works. So less than EI, bigger than EI. And then you do something recursive for the left subtree and the right subtree. You can think of this as the basic gadget that builds a binary search tree. EI is represented by a single point, and given a single point, I have essentially 2 possibilities, to the left or to the right. I want to generalize this to higher dimension, where my basic gadget is a line segment. If I have a line segment, then I don't have simply left or right. I have also above and below. In other words, if I look at a line segment as my basic gadget, a comparison with a point has 4 possibilities. Left, which means, over here, right over here, above and below. And this is very clear what's happening in the picture. Now I want to do the same thing and build a binary a search structure. Of course, it's not going to be binary because every comparison has 4 outcomes. So let's see an example of how I can use this basic gadget to build some search structure. So here the first element that I've chosen as the root of this structure is the segment S1. Okay, segment S1, comparison with segment S1 leads to 4 results: above, below, above, below, left, and right. Okay, so above takes me to region B, left takes me to region A, but below and right take me to 2 additional nodes. So let's follow. Do I have an example here? Okay, let's follow the below, for example. I compare a point with S1 and it's below, which means that it is inside this region. Okay. As you can see from the picture, if I just know that the point is inside that region, it's not enough for a point location query. So I need to do additional comparison with the segment S2. If I do an additional comparison with segment S2, left takes me to C. So now if a point is below S1 and to the left of S2, it must be inside region C. If it's below S2, it must be in the region F, and if it's above S2, then it must be region D. Note that in this case, you cannot be to the right of S2 because it's impossible. It's impossible to be below S1 and to the right of S2. Right? So by doing two comparisons in the worst case, I can find the region I'm in. So let's do another example. So let's say you're here. So this is your query time. Again, you follow this search structure. You compare the query to segment S1. So the query is to the right. So I follow this pointer. Then the query then takes me here. Then I need to compare with S2. Then the query is above S2. So I follow the above pointer and it takes me to region E, which is correct. Let's do one more example. So now if the query is here, again I start from here, compare with S1. This is to the right. It takes me here. I compare with S2. This is to the right. Takes me to region G, which is the correct result. Yeah. So you can do more trial and error if you're not convinced, but basically this structure solves point location data structure. And the query algorithm is very simple. You just compare, every node stores a line segment, and you just compare your query point, and you follow the correct pointers based on the result of this comparison. And I'm calling it comparison, but it's essentially two comparisons plus a sidedness test, whether the point is above or below the line that goes through the segment. I hope that explains what is the data structure we want to get. So this is the data structure I want to get, and then in the upcoming videos we're going to see an algorithm that builds this data structure.